Welcome to Lecture 4.5 on optimization problems for Calculus 1. What we're going to do now is look at some word problems or some actual situations where we might use what we've been learning and how to optimize. So let's kind of review what we defined as optimization. The actual definition of optimization is an act, process, or methodology of making something, such as a design, a system, or a decision, as fully perfect, as fully functional, or effective as possible. Specifically, the mathematical procedures as finding the maximum or minimum of a function involved in. So we've talked about this a little bit. What might a business want to optimize? Well, it might want to optimize its profits. But in order to optimize its profits, it might need to optimize its costs or its revenue. And again, these are different types of optimization. A business would want to minimize costs and maximize revenues so that they could maximize profit. So this is a good example of how optimization is not always just getting the biggest or the best. What about a hospital? Can you think of some things that a hospital might want to optimize? Maybe it wants to minimize the number of days staying in the hospital after a surgery. This would minimize their costs. Maybe they want to optimize the recovery time, again, the minimum days that someone has to be out of work. Minimize infection rates, maximize survival rates. What about a police department? This is very relevant right now, but certainly minimize injuries to police, minimize crime, etc. Okay, maybe maximize even their public relations. So this could be something that's not that seems unrelated, but is certainly related. Maximizing their public relations, the public's opinion of them. Okay. So we've already talked. Extrema here is just another word for optimization. So when I talk about extrema, I'm talking about a maximum or a minimum. Okay. So we've already gone through both processes of finding the local extrema. This is when, remember, we had multiple mountains and valleys in a cycle. But now we're trying to find the absolute extrema, and this is the absolute maximum or absolute minimum over a function. And we've done this in previous sections of Chapter 4. So the absolute extrema is the largest or smallest over the entire domain. And so we say f of a, notice f of a is the absolute maximum. F of a is again a y value, so when we're looking for the absolute maximum, we're looking for the y value. And we say that this is the absolute maximum if f of a is greater than f of x for all values of x in the domain. Similarly, f of a is the absolute minimum. So it's really key here that you understand this concept, that the y value is the absolute maximum or minimum. Okay? The x value tells us when or where that occurs. Maybe a number of patients, number of items created or manufactured, number of items sold, etc. That would be the x value. The y value would tell us what is the maximum profit, what is the minimum cost, etc. So look at each of these functions and see if you can determine the absolute extrema. What is the absolute maximum for A example? Now notice this doesn't give you any kind of domain, so we assume it's over all numbers. What is the absolute maximum? There isn't one, right? Because it continues going up. What is the absolute minimum? The absolute minimum is 0. But notice the absolute minimum point is 1, 0. So at an x value of 1, the absolute minimum of 0 is obtained. Okay, so it's the lowest y value, so you can look at a graph and look at the lowest part of the graph it goes to. Now let's look at graph B. Notice this is the exact same function, but we've now limited the domain. The domain now goes from 1/2 to 2. So what is the absolute maximum here? What is the largest y value? Again, remember, x tells where it occurs and y tells the value of it. So our absolute maximum is 1, and it occurs at, it looks like, 2. Okay? So our absolute maximum point is 2, 1. The x value is 2, the y value is 1, but the absolute maximum is 1. This is a really important slide for you to understand the relationship between x and y and absolute extrema. Okay, what about the minimum? Well, the minimum is the same place as it was before because the lowest part on this graph is at 1, 0. So the absolute minimum point is still the same, and the absolute minimum is still 0, the y value, Let's look at this graph again, the same function. Again, we've changed it again. See if you can figure out what the absolute max and minimum are. Go ahead and pause for a second and make sure, write it down or something. It's a good test for you to see this. It's a good visual. Hopefully it's pretty intuitive now. Well, what's the highest part of the graph? Right here at 3, 4. What's the lowest part of the graph? Here at 2, 1. And remember that the absolute max is the y value. The absolute min is is also the y value. So our absolute max is 4. Our absolute min is 1. And these are the these are the absolute maximum point or the absolute minimum point. Okay. So, whoopsie. Notice again we have the same function, but if we change the domain, we've changed the extrema. If we change the domain, these are all the same function. All we've done here in each of these graphs is change the domain. It's a really important key. Okay? So, and we talked about this before, when evaluating a function with a limited domain, as in the graphs B and C below, be mindful that in order to find the extremas, the absolutes, we need to compare both the endpoint values, as you see here in graph B, with the critical values, which are how we've been determining them using the first derivative and setting it equal to 0. Okay? A very, very important concept that you need to get. Okay. So mostly we've been finding optimum values from equations. This is pretty straightforward using the derivative test that we've learned. So the challenge in the problems to come is how to find the equation or write the equation, and students often will struggle with word problems. Okay? So the key thing here is to find the question. If you find the question, you find the variable. Always in these problems on optimization, it will tell you to optimize something. Find the best cost. Find the largest area. Find the quickest route. These are questions we're going to look at in just a second. So read through the scenario and try to find optimization words. Maximum, minimum, largest, smallest. When you find that, that's it. That is the clue or the key or the pointer towards your function. Okay? Then use variables that are relative to that. So if you're trying to find the tallest height, use h, for example. If possible, create a picture or at least a data dictionary. A picture you obviously understand. If you can draw it, draw it. This will help you. Drawing it and labeling. A data dictionary is just the idea is as you're creating variables, you write them down, or maybe even formulas. So, for example, we're going to look at something as the area of a rectangle. So you might put A equals height times width and write down this is the area of a rectangle. Just kind of writing down variables, labeling them with whatever they are, and then any formulas as well. So then your final step here, the concept here, is to write an equation which you solve for the optimal variable. So if you're trying to optimize height, you want to have h equals and everything on the other side. Okay. Now it's really key here that we get rid of all variables except for one, because we don't know how to solve any of these other types of equations yet with multiple variables. Okay. So you might have if you have two variables and you're trying to get your equation in terms of one, you will have two equations, and we'll see a couple examples of those. And then find your local. Once you've got the equation written, solved for the optimal variable, all you have to do is use your derivatives, your first derivative, to find the maximum or minimum, or to find the extrema. Okay. So here's a little anagram that I've made. Cupid. Question, picture, equation, derivative. Cupid. Question, picture, equation, derivative. This is kind of the steps or what you might want to go through. Let's read the problem. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. Immediately when I read that question, I know I've got a rectangle and it's on a straight river. I could immediately draw this picture right away. Okay? He needs no fence along the river. What are the dimensions of the field of that area? So what am I trying to maximize? What's my maximum word in there? What word in here means maximum or minimum? Largest. Largest area. I'm looking for the largest area of a rectangle. Okay? Again, we look for the extrema words, largest, smallest, max, min, etc. Okay? Can we draw it? Of course, this is a rectangle. Hopefully you can draw a rectangle even if it's crappy. And remember that I need to label it. Part of that rectangle is along a river. See if you can draw a rectangle bordering on a river. Hey, look at that. We even got some water. We need to label the sides. Now, if I was doing this, I'd obviously copied this out of the book. I would have made this length and width or something like that. I don't like using X and Y. I think it's better to use variables. Okay. Next we need equation. Okay. We have a couple equations here, right? We have the equation we're trying to solve, which is the area of a rectangle. But notice the area is written in both of these variables, x, y. And this is what I was talking about before. We cannot take the derivative of this until we get this written in terms of all x's or all y's. So what is another equation from this problem that we can write and then use to substitute? Well, the farmer needs 2,400 feet of fencing, or he has this, and he wants to make this pasture. So how would I use x and y in relation to 2,400? Well, the blue line here, the dark blue line, is his fence, right? So he has 2,400 feet of fence. So what's the equation? Well, this length plus this length plus this length equals 2,400, because that's all the fence I have. So I get 2x plus y equals 2,400. The easiest thing now to do is to solve this second equation for y, and then to substitute back into the first equation, which will get rid of y, and I'll only have x's. So if I solve this second equation for y, this is an algebraic concept called substitution. We get y equals 2,400 minus 2x. All I did was subtract 2x from both sides. And since y equals this, I'm now going to substitute this value, 2,400 minus 2x, back into the area equation. Okay? So now I have a simple equation for area that's written in terms of x and a very easy derivative to take. So all I have to do is take the derivative, set it equal to 0, and solve. And so I get x equals 600. Now, remember I want the dimension, so this is another mistake students often make. They stop here. Oh, x equals 600, I solved it, yippee, let's move to the next problem. That only gives me this dimension. What is this dimension? Well, I can put it into either of these equations, equations, and solve. I'm going to use the second one because that's my constraint. And it looks like I didn't show it here, sorry. So if I put x equals 600, I get 2 times 600 is 1,200 plus y equals 2,400 and gives me y equals 1,200. Sorry about that. Hopefully you can see that though. So again, we didn't get the dimensions. The dimensions are width and length. We only got one here, so we have to put this back into the second equation to figure out what y equals, which is 1,200. I need to fix that. Alright, so you can go back and look at that problem again. It's a good, straightforward problem and simple. We're going to move on to more difficult problems that have some different kind of constraints. Now this is an interesting problem that's pretty straightforward if I make a table. Let's read it. A travel agency will plan tours for groups of 25 people or larger. If the group contains exactly 25 people, the price is $300 per person. However, the price per person is reduced by $10 for each additional person above the 25. What size group will produce the largest revenue for the agency? Okay. Now, a lot of times we read things like this and we go, what the, right? So again, first thing is, what are we trying to maximize? Look for the maximum word. Largest. Largest revenue. Largest revenue. Okay, we're trying to maximize revenue. What is revenue? How do I calculate revenue? Hopefully you know that revenue is the income from your business, etc. So if I'm a tour travel agency, what is my revenue? For example, what is my revenue for 25 people? It's not 300, right? Revenue is the number of items times the cost of items. So I have 25 people at 300 each. How much money am I going to make? I'm going to make 25 times 300. Revenue equals, I just went blank, number, quantity times cost or price. I should say price, not to confuse. So here's a good idea to make a table, because it's really straightforward. I know that, for example, it says if the price per person is reduced by 10 for each additional person above 25, that if I have 26 people, then the price is going to be $2.90 per person. Okay, so here, while it's confusing to see and try to figure out how this works, it's a good idea to make a table and start seeing what's happening. Okay, again, remember that price times quantity is revenue. Now, it's also important not to write 26, but to write an additional person. It's even giving you the math, add a person. So the first number in the group, the price per person is 300, 7,500. If I add a person, and the reason I'm writing +1 is what I'm trying to do is get down to an equation. Remember, the next step of this is to get an equation. So I'm trying to establish a pattern. Okay. Well, the price per person, again, is going to be reduced by 10. Again, I'm not going to write 290, I'm going to write minus 10. And then when I multiply these through, 26 times 290, I get this. Okay? If I add another person, so now I've added 2 people, 25 plus 2, I'm using my base number. 300 minus 20, because if I add 2 people, the price per person goes down by 20, and here's what I get. So now if I change this number to x, what happens over here? Then I'm subtracting 10 times x. And so here I have the revenue formula in terms of the variable, which is the number of people attending. Okay? So if I get this, I can figure out, if I now have a formula for revenue based upon x, I can now find a derivative that will help me maximize it, right? So there's our equation. Again, we used the table to identify the pattern. We didn't put 26, we added 1, we subtracted the additional, and notice it's using the same language in the problem. Okay? If I multiply this 2 factors out, I get a simple quadratic equation, which again is very simple to solve for its derivative. If I set this equal to 0, I now get x equals 2.5. So max revenue occurs with groups of 27.5 people. If you put this on a test, you will get it wrong. We do not have half people on tours. Okay? So you have to be conscious of your answer as well and make sure it fits the concept of the problem. So what do? Would you just round to 28? Possibly. But you don't really know. What I would do in this case is look at on both sides of this. So figure out what is the revenue if you had 27 people. And also look at the revenue for 28 people. This would be 25 plus 2. That's why there's the 2 for the x. And 28 would be 25. So notice here the revenue is exactly the same. So in this case, the revenue is maximized when either 27 or 28 people come. Okay? So there's some good new kind of tools here about making a table. How do you make a table and not put the next number, but use addition and subtraction or what is happening here when you add a person? So you add a person, you subtract $10. You add 2 people, you subtract 20. And the idea here is you want to be able to visualize the pattern so that you can substitute in the variable for the number, so it will represent any number. Okay? Here we have a more challenging problem using geometry. Okay? A cylindrical can is to be made of 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. Okay? So we're minimizing cost. Again, look for the word. So we want to minimize the cost. Okay? In order to minimize the cost, notice what we're going to have to do is minimize the size of the can, specifically the surface area, right? The metal is what's around the can. The metal is what's around the can on top and on bottom. Okay? If we're going to minimize the cost of the metal, we have to minimize the amount of metal we use. Okay? Notice that a can's measures are height and radius. Okay? Now what is the surface area of a can? oh, sorry. I've gone the other way first. Notice that the can has to hold 1 liter of oil. Okay. Now it's asking us to minimize the cost. Height and radius are not in terms of liters, so we have to convert the volume from liters into centimeters, a measure of height or distance. Okay. So 1 liter equals 1,000 cubic centimeters. Okay. And the volume of a can is pi r squared h. Okay, which is the area of the top times the height. It's almost like a rectangle, right? Okay, or a cube, I should say. All right. So the surface area, notice for this can, we have a metal top, we have a metal bottom, and then we have the metal around. Now, you may not remember, but if you cut the can open and the part around the can, if you flatten it out, it's just going to be a rectangle. So the surface area for the can is actually 2 circles plus 1 rectangle. Well, it's easy to see from this diagram, since we're given the radius, or our radius is our variable. The area of a circle is pi r squared. Since the distance around the can is the distance around the top or the bottom, or the distance around a circle, notice that one measure of this can is 2 pi r, and then of course it's the height tall. So here's our formula for area. 2 circles, so 2 times pi r squared plus 2 pi r h, the height times the width. And again, the width is 2 pi r because it's the length around the can. All right. Now this is what we're trying to minimize, but again we have 2 variables. But notice here in the blue equation, 1,000 equals pi r squared h, we can easily solve for h by dividing both sides by pi r squared, and then we can substitute that in here, and we lose the h, and we have it written in terms of 1 variable. Always have to rewrite these equations in terms of 1 variable. So by substituting that in, we get area equals 2 pi r squared plus 2,000 divided by r. Okay? This is just some basic algebra. You should be able to do this part here. Again, these are pretty straightforward derivatives. If we take the derivative of this, we get 4 pi r minus 2,000 over r squared. If we set this equal to 0 and solve, we get 4 pi r. What am I saying here? Yeah, here we go. We add 2,000 over r squared to both sides, so we get this is equal to 0. We multiply, we cross multiply, so we get rid of the fraction, and we get 4 pi r cubed equals 2,000. And then dividing by 4 pi, and then taking the cube root, we get the radius equals 5.42 centimeters. I could have showed this, but this is all algebra at this point. Set this equal to 0 and solve for r. You should be able to do that. Again, add 2,000 over r squared to both sides, and then you'll have 4 pi r equals this fraction. Cross multiply, and it should be simple to solve. Again, we have to go back and find h, but since we know that h is 1,000 over pi r squared, and we have r, this is quite simple to do. So these are the measures of our can that will minimize the cost of the metal. All right, let's look at an even potentially more challenging problem. This is a great one for a picture, and it's a little bit confusing, so it's a good idea to start off. All right. So first I'm going to just kind of skim through here and see what I'm trying to find. Blah, 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 blah. This is hard because I don't see any large words. I don't see any small words. But notice it says, here's the question. I have a question mark, so that's a good place to go. Look for the question. If he can row 6 kilometers per hour and run 8 kilometers, where should he land? So I'm looking for some kind of spot to reach B as soon as possible. So we're trying to optimize some kind of speed, it looks like. We're trying to optimize speed so he gets someplace fast. So we're optimizing speeds. We're minimizing travel time. So I'm sorry, it looks like gets there as soon as possible, so that's the smallest amount of time. So we can't optimize speed because the speed is given. I'm sorry. Okay? Gets there as soon as possible. What does that mean? In as short a time as possible. So we're minimizing travel time as soon as possible, as short a time as possible. Now let's go back. A man launches his boat from point A on the bank of a straight river. So draw a straight river, you know, 2 banks. Put a point A there. The river is 3 kilometers wide. So directly across from A is 3 kilometers. Put a little measure there. And he wants to reach point B 8 kilometers downstream on the opposite side. So if A is on one side and it's 3 across, go down 8 and put point B. You now have 2 measures. You have 3, the width of the river, and 8, the opposite side of the river from A to B. He could row his boat directly across the river to point C. That's the point we already made, directly across from A, and then run to B. Or he could row directly to B. So we can draw a line there, which is now we have a right angle, a right triangle. You're saying, wait, where is all this stuff? I want you to try to draw this. And it's a really good idea for you to do that before looking at it. So see if you can do that. Or you could row to some point D between C and B and then run to B. So we have this right triangle, A, C, B, and he could row directly across and run down. He could row directly to B, or he could go to some point D in the middle there. So put a point D in the middle. Alright, so now you can see what I'm talking about. Draw a river, put your point A on first. It tells you the river is 3 kilometers wide. Mark that. It tells you that there's another point 8 kilometers down from the point across the river. Mark that, and that's point B. It then tells you he could row across to C, directly across, mark that, and run to B. Or he could row directly from A to B. Or he could row to some point in the middle and then run the rest. So we have 3 things here we have to consider. Okay? But let's figure out, first of all, we're given measures here, distance. Okay? We are given his speed. If we're given speed and distance, and we're trying to figure out time, what is the formula? This is a simple formula. If you're driving to Austin at 50 miles per hour and it's 150 miles, how long does it take you? Time is equal to distance over speed. Distance over speed. You're driving to Austin 150 miles away at 50 miles per hour, it takes you 3 hours. It's a simple formula. So the total time that it takes for him is the time it takes rowing plus the time running. So the distance rowing, and we're going to do this point D. We can figure out the endpoints pretty simply, but let's do the formula for this point D. So notice here I've made this point, this value from C to D, x. Alright? So if C to D is x, then from D to B would be 8 minus x. 8 minus x. Okay? So his distance rowing from AD would be, notice I have a right triangle, 3 squared plus x squared equals this distance squared, so I take the square root of that. Square root of x squared plus 3 squared, which is 9. Plus the distance he runs, which is simply 8 minus x, because his total distance is 8, this is minus x, all over their speed, and it tells you his speed rowing is 6, and his time running is 8. Okay, so here we have an equation for time. It's very simple to take the derivative of this. We can take the derivative of each piece. Notice here the derivative is simply negative 1/8. If you divide this and make it into 2 fractions, you get plus 1 minus 1/8 x. And here you can take the derivative of a radical pretty simply. Okay? If we set this equal to 0, you will get 9 over the square root of 7. I'm not going to do this algebra. You should be able to solve this by setting this part of the equation equal to 0, or x equals 3.4. Now remember, x is the distance. Okay? X is the distance. So we have to put this back into this equation to find the time. Okay? Back into this original equation here to find the time. So when we plug 3.4 into this equation, it would take him 1.33 hours to row to D and to run to B. Now we have to compare this with rowing and running, or simply rowing. Okay? Well, what is the distance AC? Well, that's 3. Rowing, I'm sorry, we're going to do rowing all the way first. Rowing all the way is the distance AB. Again, notice what we have here is the Pythagorean theorem, 8 squared plus 3 squared equals this distance squared. So we take the square root. And that's all we need is this distance, right? Divided by his speed that he rows. So distance divided by speed, and we get 1.42 hours. So this is not our answer because we're trying to minimize the time. So let's look at what happens when he rows and then runs. Well, again, the distance rowing here is these are actually easier. The distance rowing is 3 divided by the speed rowing. Distance by speed. 3/6 rowing. Distance running 8 divided by his speed running 8, and we get 1.5 hours, which is even longer. So the optimum situation is for him to row 3.4 kilometers downstream. Okay, I know that was a little bit involved. I would suggest you go through it again. If you take your time and walk through it, none of these formulas are very complicated. It only uses the Pythagorean theorem. But this picture was key. What happens often is students read all this data and they get overwhelmed. If you start from the beginning, I'm on a straight river bank. Draw a river from point A on the bank. Point A on one side. It's 3 kilometers wide. Start drawing the pieces and quit trying to eat the whole thing. When you read a whole problem, you get overwhelmed. It's as if you're eating a beef steak and you try to put the whole damn steak in your mouth. Don't do that. Take a bite at a time. Point A on a bank of a straight river, 3 kilometers wide. Point B, 8 kilometers downstream on the opposite bank, 8 kilometers downstream, opposite bank. So each of those pieces can be done relatively simple. So you try these problems, practice many of these problems. These are key. These are some of the more challenging problems in this course.